In this video, I will talk about another application of Taylor and Maclaurin, mainly Maclaurin series, and in particular how to integrate with power series. And we're going to be using the knowledge of some of the functions power series representations, such as presented in this table. And let's take a look at the following problem. Let's say we have to find an integral of the following function. And we know, as a matter of the fact, that the function e to the power x squared and similar functions don't have the antiderivative in closed form. So that means if we have to find the definite integral, we cannot use the fundamental theorem of calculus simply because we don't know what the antiderivative is. So it's a common, such question as this one is a very common in probability and statistics. So how can we approach this problem other than doing some numerical integration such as Simpson's or any other? So let's take a look and see what can be done. And the first thing we're going to do is we're going to remind ourselves the following fact. And in particular, I guess not in particular, but anyway, we're going to remind ourselves the following fact, that the power series representation of e to the x is this, meaning that we can find the power series representation of the integrand function now, the function that is inside of the integral, by simply replacing x with negative x squared over 2. And of course, if desired, we can try to keep track of the nth term of this series. So we just plug in what negative x squared over 2 to the power n over n factorial. And while it is impossible for us to find the antiderivative of the original function, it is possible for us to integrate this function's power series representation term by term. So to do that, we're just going to simplify it right first. So we have 1 minus 1/2 x squared plus 1/8 x to the 4 minus, we have 8 times 6, 48 x to the power 6, etc. With respect to x, which is the integral of negative 1 to the power n over 2 to the power n factorial x to the power 2n. I forgot, I lost the sigma. And here's what's going to happen. We can now integrate this as just like we would integrate any polynomial function. So the antiderivative of 1 is x, and the derivative of x squared is 1/3 x cubed, and so on. And in general, this can be written as so antiderivative of this is going to be 2 to the n and factorial times 2n plus 1 x to the power 2n plus 1. And when we remember, when we integrate, we also have the constant of integration, which I will label as a, and a is equal to f of 0, but f of 0 in this case is 1. So also, I guess the first one also we have to have the constant of integration. So what do we have here? We have found the power series representation of the general antiderivative of this function. We don't know what this function is. We don't know what this function, what this power series converges to, but we did found it, and there is a application of what we have done. So for example, if we were to make this integral a definite integral, so let's say now we're looking for the integral from 0 to 1 of this function, we, without knowing the function that is an antiderivative, we can use the power series representation of that function and what we can do is we can evaluate this power series representation between 0 and 1. And this would allow us to not accurately not find the exact value of this integral, but at least do a good approximation. So evaluating this at 1 gives us this. Etc. And evaluating this at 0 will give us 1, and all other terms will be, of course, 0. And now computing this, what do we have? We have, if we make the common denominator, I guess we just have to compute this with a calculator. So to check my work, I'm just going to, not to check my work, but to do the computations, I'm just going to use Wolfram Alpha. But again, these are the type of computations that any calculator can do. So approximately we estimate this to be equal 479 over 560. Which is approximately equal to 0.855. And of course, without technology, we wouldn't know what the exact answer is. But right now, we can take advantage of technology and actually plug this problem, this whole problem, into the calculator. And see what the actual answer would be. So integrating from 0 to 1, this function, let's see what we get. So we hope that the answer is negative, I'm sorry, not negative, but 0.855. And it looks like, yep, we definitely got the first three digits correct. So this was an example of how to use power series when it comes to integrating functions which don't have the general antiderivative in closed form. Let's do another example. This time we'll just do the indefinite integral. But consider the following problem, which is not easy if you don't know any other techniques of integration. In this case, we're going to recall the power series representation of ln of 1 minus x, ln ln of 1 plus x is equal to 1 minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4, etc. So this is the power series for ln 1 plus x. Now, if we want to obtain the power series representation for ln of 1 minus 4x cubed, then we just have to take this power series and replace x with negative 4x cubed. Missing something here. This should be x, because when n is 0, then this should be 1 in that power series representation. So when n is 1, we get 1. Yes, there you go. So this should have been x, not just 1. Apologize about that. So instead of x, we put negative 4x cubed. And now we see, right? So negative 4x cubed, etc. And while integrating, the original function may not be an option, we can definitely integrate this series. So let me just finish writing this out. 8x to the 6 minus 64 thirds x to the power 9, etc. The general term, let's see if we can write it out. So we have negative 1. We have negative 1 to the power n plus 1, negative 1 to the n. So it's going to be negative 1 to the power 2n plus 1. So it's always odd. So we're always going to have negative 1 here. And then we have 4 to the power n over n times x to the power 3n. So when n is 1, we get negative 4. When n is 2, we get 16 over 2. When n is 3, we get 64 over 3, and so on. So this seems to be right. And now when we integrate this function, we simply integrate the first few terms, and we can also integrate raise this up a little. we just integrate this term by term. So we have negative 4 to the n over n, x to the power 3n dx. So the first few terms of this will be negative x to the 4 minus 8 7x to the power 7 minus 64 over 30 x to the power 10, etc. So these are just the first few terms of this series. In general, this series can be written like this. We're going to have another constant of integration, a, but a will be equal to f of 0, which is in this case 0. So we're not going to have any constants of integration here, of course. Basically what we're about to write has to match what we have already written, just it's going to be a general form of it. So we have negative 4 to the power n over n times x to the power 3n plus 1 divided by 3n plus 1, so it just comes right over here. So we didn't find the function because there is no function that can be written in closed form that is an antiderivative of the original function, but we did find its power series representation. So if this was a definite integral, then we could have found this definite integral. So for example, let's just make it an integral from 0 to 1, although we can't, because at 1 it may not converge. So let's just make it an integral from 0 to 1/2, maybe. Actually, it doesn't matter. So basically, if this was 0 to 1/2, then it will be a definite integral, and then we would be able to compute the definite integral by simply evaluating this between 0 and 1/2, which we are not going to do, but you should be able to see how the power series can be used when integrating certain functions which don't have antiderivatives in closed form.